Analyze the continuous beam shown in figure by method of moment distribution. Here this one is the given diagram. This one is A to B, A to D. A to B is 4 meter subjected to 50 kilonewton per meter UDL. B to C, this is 2 meter, this is 4 meter and is subjected to 120 kilonewton at a distance of 2 meter from B and 4 meter from C. This one is 80 kilonewton. CD is of span 5 meter at a distance of 2.5 meter from each end. A point load of 50 kilonewton is acting. First we have to calculate to analyze this by using the moment distribution method. The first step is we have to calculate the fixed end moments in various spans. Here the fixed end moments M of AB. M of AB, here we are calculating from this end. This moment is anti-clockwise. The fixed end moment is anti-clockwise, and then that is the minus WL square by 12. Here W is 50, L is 4, that is 66.66, that is negative. Then from this end, MFBA, that is WL square by 12, that is clockwise, hence that is plus 66.66 kilonewton meter. For the second span, BC, here W is 120, A is 2 meter, B is 4 meter, MFBC, that one is anti-clockwise, hence negative. W is 120, WAB square by L square. W is 120, A is 2 meter, B is 4 meter, divided by L is 6, that is 120 into 2 into 4 square divided by 6 square, that one is minus 106.66. From the other end, MFCB, that is WA square B by L square. W is 120, A is 2, B is 4, L is 6, then that is 53.33 kilonewton meter. For the last span, CD, it is subjected to point load at the center. The fixed end moment, that is minus WL by 8. At the left end, that is minus 80 into 5 by 8, that one is minus 50 kilonewton meter. From the right end, that is MFDC equals 80 into 5 divided by 8, that one is clockwise, that is 50 kilonewton meter. The second step is to calculate the distribution factor for the intermediate joints only. Here there are two intermediate joints. One is B, one is C, that we have discussed in the previous video. Here we have to calculate the distribution factor. Here joint B and joint C are the two joints. At this joint B, two members are connected. One is BA, one is BC. Similarly, at joint C, two members are connected. One is CB, one is CD. Here member BA, joint K equals, that is stiffness factor, that one is I by L, summation K, that is summation of the relative stiffness at that joint, summation K. Distribution factor is given by relative stiffness for the member divided by summation of the relative stiffness at that joint. Here for this one, with respect to B, A is continuous or fixed. This one is fixed, hence K equals I by L. That is I equals there is single I. If the moment of inertia varies, then you have to write here the moment of inertia is same throughout the length of the continuous beam. Hence K equals I by L, that is 4 meter. Similarly for this span, with respect to BC is continuous, there is a continuity B and C, hence K equals I by L. L is 6 meter, I by 6. Summation K, I by 4 plus I by 6 equals 0.417 I. Then the distribution factor for BA, that one is KBA divided by summation K, that one is 0.6. KBC divided by summation K, that one is 0.4. Then come to the next joint. Here two members are connected, one is CB, one is CD. Then K for the member, that is relative stiffness for CB. With respect to CB is continuous, hence K equals I by L, where L is length, that is 6 meter. For this one, that is I by 6. Similarly, for the next member, that is CD, with respect to CD is continuous or fixed, this is fixed, hence K equals I by L. L is the length of CD, that is 5 meter, therefore K equals I by 5. The summation K, by adding this to I by 6 plus I by 5, that is 0.367 to I. Then the distribution factor for CB, KCB divided by summation K, that one equals 0.46. KCD divided by 0.3672, that one equals 0.54. After the calculation of the distribution factor, now we have to draw the moment distribution table. Here, this one is start from the joint A, B. At B, two members are connected. One is BA, one is BC. Then C, CB and CD are the two members. D, DC is the member. Here the distribution factors that what we have calculated in the previous step, that we have to write. For BA 0.6, for BC that is 0.4, CB that is 0.46, CD 0.54. For the end members, there is no distribution factor. Then we have already calculated the fixed end moments in the first step. That one you have to write, that is minus 66.66 for AB. Then for BA, that is 66.66. For BC, that is minus 106.66. For CB, that is 53.33. For CD, that is minus 50. CD, that is plus 50. Here at B, by observing this at joint B in the slope deflection method, we have studied that at joint B must be in equilibrium. That means some of the moments must be 0 at joint B. Then here by observing these two moments, here this one is plus 66.66, this one is minus 106.66. Here there is a difference of, instead of 0, there is a difference of minus 40. Minus 40 is distributed among the two members such that the joint B must be in equilibrium. You have to distribute minus 40 and you make it 0, that is balance. By balance means by adding or subtracting the moment of same magnitude with opposite sign. Here this unbalanced moment is minus 40, then we have to add plus 40. Plus 40 into 0.6, that one is 24 for BA. Plus 40 into 0.4, that is 16 for BC. Then come to the next joint. Here the unbalanced moment is 53.33 minus 50, that is plus 3.33. You have to balance this by adding minus 3.33 and we have to distribute among these two members, that is minus 3.33 into 0.46, you will get minus 1.53, minus 3.33 into 0.54, that one is minus 1.8. Here if you observe these values in the box in this rectangle, the summation of all these moments must be equal to 0. Similarly here also the same thing. If we add, this one is known as balancing of the unbalanced moment at the joint. Then carry over. Here from B, here this end is fixed, this end is fixed, this end is continuous. Then there is a carryover from B to A. There is a carryover from B to A. Similarly, there is a carryover from B to C. B to C. 50% of the moment is carried over with same sign. 50% of the moment is from B to A. 50%, that is half of 24, that is 12. Similarly, from B to C, here 50% of 16, that is 8, is transferred to CB. Similarly, at joint C to B, there is a carryover, there is continuity. C to B, C to D, there is a carryover since this one is fixed end. Therefore, here from C to B, there is a carryover. 50% of this one is minus 1.53 into 0.5. That one is minus 0.765. With same sign, you have to transfer. 50% of that is carried over. Similarly, from C to D, there is a carryover that is minus 0.9. Then again, in the second cycle, there is an unbalanced moment at joint B and joint C. We have to make it balance, make the joint balance by adding or subtracting the moment of same magnitude. Then here balancing in this, here you have to balance this, that is here this one is minus 0.765. Here we have to balance this. To balance this, we have to add 0.765, that is positive. Then we have to distribute that among the two members. One is BA, one is BC. Then 0.6765 into 0.6, that is 0.459, that is positive. Similarly, 0.765 into 0.4, that one is 0.306. This is balanced. Then come to the next joint. Here there is an unbalanced moment of 8 kilonewton, that is positive. We have to distribute, we have to balance this by adding minus 8, and we have to distribute the moment among these two members, that is 8 into minus 8 into 0.46, that one is minus 3.68, minus 8 into 0.54, that one is minus 4.32. Here in the second cycle, if we add all these things in this rectangle, you will get 0. Similarly, at this joint C, you will get 0. Next, carryover. Here 50% of the moment is again carried from B to C, B to C, B to A. Similarly, 50% of the moments are carried from C to B and C to D, that is from B to A, half of 0.459, that one is half of 0.459, that one is 0.23, is carried from B to A. Then from B to C, half of 0.306 is transferred to CB, that one is 0.153. Then here C to B at the joint, here C, the carryover from C to B, that is half of minus 3.68, that is minus 1.84. So then C to D, there is a fixed support, there is continuous or fixed, then half of this one is minus 4.32 by 2, that is minus 2.16. Again, there is an unbalanced moment at joint B and C. Then we have to distribute, that is in the third cycle, to make it balance, that is minus 1.84 is distributed among the two members at that joint, that is one is BA, one is BC. Then here minus 1.84 into 0.6, you will get plus minus 1.84. We have to add plus 1.84. plus 1.84 into 0.6, that is 1.104. Then minus plus 1.84 into 0.4, that one is 0.736. Now this is balanced. This joint is balanced. Come to the next joint, that is 0.153 is the unbalanced moment at joint C. To balance it, add minus 0.153 in the ratios, that is 0.46 and 0.54 among the two members CB and CD, that is minus 0.153 into 0.46, you will get minus 0.07. Similarly for this, that is minus 0.08. Now again we have to carry over this moment from B to A, B to C, there is a carryover, C to B and C to D, there is a carryover. Here 1.104, 50% of this moment is carried from B to A, that is half of 1.104, that one is 0.55. Similarly, from B to C, there is a carryover, that is half of 0.736, that is 0.368 is transferred to CB. Then C to B, there is a carryover. Here, half of this one, that is minus 0.035 is carried from C to B. Then from C to D, there is a carryover. Half of this one, that is minus 0.04 is transferred to joint D. Then here, by observing this, again there are in fourth cycle, there are again unbalanced moments. Here the moment is 0.035 at joint B. You have to balance this by adding plus 0.035 and distribute among the two members, that is BA and BC. Then 0.035 into 0.6, that one is 0.02, and 0.035 into 0.4, that is 0.015. Here these two moments are positive, this one is negative. By adding all these things, that is the joint is balanced, or the algebraic sum of the moments at this joint is 0. Similarly, at joint C, there is an unbalanced moment, that is 0.368. Distribute and balance this by adding minus 0.368, and it is divided into, that is minus 0.368 into 0.46, that is minus 0.169, and minus 0.368 into minus 0.54, that is minus 0.193. Again, you have to carry the moments to the next joint, next cycle. In the next cycle, here, if you observe this, from B to A, there is a carryover of half of this moment, that is 0.02 divided by 2, that is 0.01. Similarly, here 50% of the moment is carried from B to C, that is plus 0.015, half of that one is 0.0075. Then similarly, minus 0.1669 is the moment at C. Then transfer this, half of this one is carried from C to B, that is half of that one is minus 0.085. Then from C to D, there is a carryover. 50% of this moment is carried from C to D, that is minus half into 0.193, that one is minus 0.099. Here the terms are very small, the fractions, the values are very very small. Now we can close this for this cycle. Now we have to get the final moments. The final moments are by adding all these things, that is fixed end moment plus the remaining things, you will get the final moment at AB is minus 53.89. That is negative, means that one is anti-clockwise. Then for BA, that one is 92.24. By adding 1 2 3 4 5 6, that is 92.24. This is the final moment at BA. Then BC, by adding these things, you will get minus 92.12. Here, by observing these two values, there is a small difference. That should be, in terms of fractions, that should be okay. Here, if the difference is more, then you have to recalculate. Here in CB, here by adding all these things, you will get 56.40. This one is positive, that means that is clockwise. Then for CD, by adding all these things, that is minus 56.399. That one is anti-clockwise, or that is negative. Then finally, the end moment at D, that is FD, MDC, that one is 46.80. Here, to draw the bending moment diagram for this one, we have to draw the bending moment for this one. First, we have to draw the diagram like this. Here, this one is A to B, this one is A to B. This is subjected to 50 kilonewton per meter, and the length of A to B is 4 meter. Here the moment acting, the support moments, this one is 53.89 kilonewton meter, this one is 92.24 kilonewton meter. Here both are hogging moments. Both the support moments are at A and B, both are hogging moments. Similarly, for B to C, here the support moment is, this one is anticlockwise 92.24 and this one is 56.40, this is clockwise. Here again both the support moments are hogging moments. Then for this joint, for this member, that is for this span CD, here this one is 56.40, this is anti-clockwise, and this one is 46.80, that is MDC, that is clockwise. Here by observing these all the support moments, all the moments are hogging moments, all the moments are hogging moments. To draw the bending moment diagram, first draw this datum line or reference line. We can represent the hogging moments above the reference line. Here draw the ordinate of this one, that is 53.89, and at this support 92.24. By joining this by a straight line, you will get the support moment diagram in span AB. Similarly, for this span, draw the bending moment ordinate. This one is already we have drawn. This ordinate is 56.4, this one is hogging. We can represent this above the reference line or datum line. Then join these 2 points to get the support moment diagram. That one is negative diagram. Then here for CD, this one is 56.4. Here draw an ordinate of 46.80 kilonewton meter, that is also hogging. Join these 2 points by the straight line. Here now we will get the support bending moment diagram. Support moment diagram. We have to overlap on this the simply supported beam bending moment diagram. Here first one, first AB, A to B, there is A to B, there is UDL, it is subjected to UDL of intensity 50 kilonewton per meter. Then the maximum bending moment in the simply supported beam, at the support the bending moment is 0. At the center the ordinate is maximum, that is 50 into L square by 8, WL square by 8, that one is 100 kilonewton meter. This one is the sagging moment. Here we have to draw this sagging moment. By overlapping this, you will get this is the maximum ordinate. Here the shaded portion, this one is positive moment, this one is negative moment. The shaded portion is the net bending moment in span AB. Similarly, for the span BC, it is subjected to a point load of 120 kilonewton meter at kilonewton at a distance of 2 meter from B, 4 meter from C. Then this bending moment is WAB by L. Here A is 2 meter, B is 4 meter, L is 6 meter, W is 120. 120 into 2 into 4 divided by 6. That one is 160 kilonewton meter. This is the maximum bending moment. Again, at the support, the bending moment is 0. Then join the ordinate from this point to this point, joined by a line, straight line. The variation is straight line. And again, join this point to this point by a straight line. The variation is a straight line. The bending moment diagram is a triangle. Here similarly for this also, here the point load is acting at the center. The maximum bending moment due to the point load at the center in a simply supported beam is positive, that is 80 into WL by 4, that is 80 into 5 by 4. You will get a triangle. That one is 100 kilonewton meter. Here the shaded portion, that is by after overlapping you will get the net bending moment diagram.